I welcome you all to the session of engine system and performance, and today we shall solve one numerical problem on turbocharger. In the last class we have discussed about turbochargers. We had seen the operation of turbocharger. As such, we have discussed the constructional feature of the turbocharger unit, and then of course what are the advantages of this particular unit in the context of engine operation, and also we have identified problematic issues with this unit as well. So, today we shall solve a numerical problem, and that problem is essentially on turbocharger. If I can recall correctly, in the last class we have solved one numerical problem on supercharger. So, the basic difference between these two units is supercharger essentially is having one compressor, centrifugal compressor, and then depending upon the requirement there may be one aftercooler to be installed at the exit of the compressor, because the compressed air will be having high temperature and the temperature of air will increase in the subsequent stages. So, that high temperature may lead to detonation or knock for the SI engines, but it rise in temperature may not be problematic, rather a problematic issue for the CI engines. So, in a supercharger the compressor is driven by consuming or borrowing certain amount of power from the engine shaft, while in a turbocharger or turbocharging unit compressor is driven by a small turbine, while the turbine is rotated by the exhaust gases, to be precise by exploiting the kinetic energy of the exhaust gases. So, if I write here most important difference between these two unit, supercharger compressor, typically this compressor is a centrifugal compressor. Compressor is driven by the energy of the engine. So, by the energy of the engine, or rather by the energy of the engine that is at the available at the output shaft. So, compressor is driven by the energy of the engine which is available at its output shaft, while for the turbocharger or turbochargers the small compressor is driven by a small turbine, and turbine is driven or operated by the exhaust gases. So, this is the fundamental difference between these two units. Certainly you can understand if we can really use the energy which will otherwise will be lost by the exhaust gases to the ambience to drive a small turbine, and if we can connect the compressor, rather if we can have one common spindle, and if both rotating elements, that is or rotating devices, are connected to a common shaft, then compressor can be driven. So, while for this case you can see which is available at its output shaft. So, certain amount of output power will be again used to run the compressor. So, we need to compromise with the engine efficiency. So, now let us solve the numerical problem. As such we have solved one numerical problem on supercharger in our previous class. but today the sole objective of solving this problem is to get acquainted with the performance map. So, this is basically performance map of the compressor. Okay. So, let me first read the problem statement. A naturally aspirated 4-cylinder 4-stroke engine has the following specification. So, engine is a 4-stroke cycle engine and 4-cylinder. Total displacement volume is 2316 centimeter cube. Compression ratio is given 9.5 and it produces a BHP of 83 kilowatt at 90 RPS. So, when engine is rotating at 90 RPS, the brake horsepower produced by the engine is 83 kilowatt. Compression ratio is given 9.5 and the displacement volume is also given 2316 centimeter cube, fine. For this naturally aspirated engine, inlet manifold conditions are 1 bar and 310 Kelvin. So, that means when the engine is naturally aspirated, so there is no any supercharger or turbocharger. So, the ambient conditions are 1 bar and 310 Kelvin. Volumetric efficiency of the engine is given 84% and mechanical efficiency is 90%. So, essentially the volumetric efficiency and mechanical efficiency, these two efficiencies are the efficiencies when the engine is a naturally aspirated engine. Okay. The next para is a turbocharged version of the engine utilizes a compressor whose performance map is shown in the following figure. So, as I already mentioned, this is the performance map of the compressor and the compressor is now there in the turbocharging unit. Estimate the brake power of the turbocharged engine at 90 RPS. So, when the same engine is now getting operated by a turbocharger or turbocharging unit, we need to estimate brake power when the engine is running at 90 RPS. If the compressor pressure ratio, that is P2 by P1. So, essentially you know by this time that compressor is used to raise the pressure. So, the pressure ratio is very important parameter for the design of compressor and the pressure ratio is given P2 by P1 equal to 1.5. So, that is given. The compressor is followed by an intercooler essentially to take off certain amount of heat or temperature of the compressed air, or otherwise it will lead to another problem, that is knock, because probably the engine is a SI engine. From the statement we can understand. It is not universal but true that aftercooler will not be there for the CI engines. Typically for the SI engines aftercooler is a must, but for the CI engines depending on the requirement aftercooler may be there. So, the compressor is followed by an aftercooler and its exit temperature is 340 Kelvin. Volumetric efficiency is 91% and mechanical efficiency is 88%. So, essentially when the engine is not a naturally aspirated engine, rather engine is turbocharged, the same engine is giving volumetric efficiency 91% and mechanical efficiency 88%. So, you can understand we can little bit increase the volumetric efficiency, that is what is the objective of having this unit. So, the amount of mass or the mass that should be consumed by the engine during intake stroke or greater mass of or greater amount of air can be drawn into the engine cylinder, that is why this turbocharging unit is there. Now, assume that the net indicated power is proportional to the flow rate and that is given by this relation. So, we will be using this. What is the compressor speed and its efficiency? The first part that we need to answer, and second part is, so the first part is basically we need to estimate the brake power of the turbocharged unit. Second part is to estimate the compressor speed and its efficiency and what is the heat transfer to the intercooler. So, all these things are very important to know. So, let us now solve the problem. So, if we start solving the problem, so let us start from here. Solution. So, we can see that for the naturally aspirated engine NA. So, I will be writing NA for the naturally aspirated engine, and TC for the turbocharged engine. So, these two will be using for the naturally aspirated engine indicated horsepower, right, that is I am using IHP NA that equal to, because it is given you know that 83 kilowatt is the brake horsepower. So, indicate brake horsepower by indicated horsepower is the mechanical efficiency, that we know. So, indicated horsepower should be brake horsepower divided by mechanical efficiency, that is 0.9. So, this is kilowatt unit and it is coming as 92.22 kilowatt. So, that is the indicated horsepower for the naturally aspirated engine. Okay. So, from here we know BHP of the naturally aspirated engine equal to 83 kilowatt. We have calculated IHP, from there we can easily calculate FHP of the naturally aspirated engine equal to IHP minus BHP for the naturally aspirated engine, and if we calculate it, it is coming as 9.22 kilowatt. So, you can understand 9.22 kilowatt, this it is getting lost due to the frictional effect. Okay. Fine. So, for the if we go to the next slide, let me mention here, for the turbocharged engine volumetric efficiency is 91%, that is estimated, and mechanical efficiency is 88%. Certainly we can see that when the engine is turbocharged, volumetric efficiency increases, though we need to compromise with the mechanical efficiency, because mechanical efficiency has reduced by 2%. Fine. So, if we go to the next slide, then we can write for the turbocharged engine volumetric efficiency is 91%, that is 0.91, okay, and this inlet pressure, that is we need to know from the problem statement itself. See, for the turbocharged engine, the manifold condition, that is air temperature and air pressure at the inlet manifold will be dictated by the exit condition of the compressor. Though there is an aftercooler, but see, we can understand the compressor pressure ratio is 1.5. Certainly, if the ambient pressure is 1 bar, then our pressure at the exit of the compressor will be 1.5 bar, and that is the manifold condition for the turbocharged engine. So, if we write here, for the turbocharged engine, this inlet pressure equal to 1.5 bar, and Ti that is given, the compressor is followed by an aftercooler and the exit temperature is 340 K, and exit temperature of air or air temperature at the exit of the compressor is equal to the air temperature at the inlet of the engine. So, that is 340 K. So, this is 340 Kelvin. So, given this data, what we can do, this is for the turbocharged engine. Now, for the naturally aspirated engine, we can write volumetric efficiency equal to 84% and Pi equal to 1 bar and Ti equal to 310 Kelvin, right. So, these are the statement. So, for the naturally aspirated engine, inlet manifold conditions are this: volumetric efficiency 84% and mechanical efficiency 90%. So, these are the data given. Now, it is given, the most important part of this problem is to follow this line. The net indicated power is proportional to the flow rate, and that is mathematically described by this relation. If we rewrite this relation, we can write that indicated mean effective pressure for the turbocharged engine divided by indicated mean effective pressure for the naturally aspirated engine, that equal to basically mass flow rate. So, eta V P I by T I for the turbocharged engine divided by eta V P I by T I for the naturally aspirated engine. So, this is nothing but the mass flow rate. Okay. So, if we write, we know all these quantities, because for the turbocharged we know eta V equal to 0.91 and then Pi equal to 1.5 bar. Then if I write here, this Ti for the naturally aspirated engine will go off. So, it is 310, then it is coming as 0.84 into pressure is 1 bar into this is 340, and the ratio if we calculate, you will get it 1.481. So, this is the ratio of indicated mean effective pressure for the two engines. If we go to the next slide, so you know that indicated horsepower is proportional to indicated mean effective pressure, because this is a mean effective pressure. So, the work done on the piston by the gas is essentially dependent on the indicated mean effective pressure. So, this if it is the case, then we can write IHP for turbocharged by IHP of naturally aspirated equal to 1.481, because this would be IMEP TC by IMEP NA, and the ratio already you have calculated, that is 1.481. From there we can calculate indicated horsepower for turbocharged engine, that is 1.481 into, if we go to the previous slide, we have already calculated indicated horsepower for the naturally aspirated engine, that is 92.22 kilowatt. So, if we go to the next slide, just we can write 92.22 kilowatt, and the answer is 136.63 kilowatt, that is the indicated horsepower of the turbocharged engine. It is given, let me again go back to the problem statement. It is given that even when engine is turbocharged, engine speed is 90 RPS. So, the engine speed is not getting changed. Essentially, this line is giving us a clue that frictional horsepower will remain unaffected. So, if we go to the slide here, then since speed remains constant at 90 RPS, right, the frictional horsepower is same for both the conditions. Okay. So, that means we can easily calculate brake horsepower for the turbocharged engine is this IHP of turbocharged unit into mechanical efficiency, because brake horsepower by indicated horsepower is the mechanical efficiency. So, this is nothing but, if I write, this is 136.63 and mechanical efficiency is 88%, that is 0.88 kilowatt, and if we calculate it, the value is coming as 120.23 kilowatt. So, this is the brake horsepower. Let me go back to the problem statement once again. The first part of this question was to calculate or estimate the brake power of the turbocharged engine at 90 RPS. So, that we already estimated, and this is the first part. So, that is 120.23 kilowatt. So, that is the answer for the first part. Okay. Had we considered maybe frictional losses, because both of them are at same speed. So, we did not take into account the frictional losses, that will be that may even affect the brake horsepower for the turbocharged engine, but good thing is that the speed is remaining same. Okay. So, if we go to the next slide. So, next we will have to determine the mass flow rate of air for the turbocharged engine. Mass flow rate of air for the turbocharged engine. The sole objective is to equip or install this particular unit is to increase the mass flow rate. So, basically greater amount of mass can be consumed. So, if we need to take this, what we need to do, the inlet air density. So, inlet air density we have to calculate first, and that inlet air density rho I for the turbocharged condition, that is Pi by RTI, right. So, Pi, that is the inlet manifold condition for the turbocharged engine, is basically pressure of the air at the exit of the compressor, that is 1.5 bar into 10 power 5 Pascal divided by 287, that is R, that is given, and Ti equal to 340, that is the temperature Kelvin. So, that if we calculate it, you will get the value of density or inlet air density for the turbocharged case is 1.537 kg per meter cube. Okay. This is the density. So, knowing the density, we can calculate mass flow rate of air, right. For the turbocharged case, m dot A for the turbocharged case TC, that would be equal to rho I into V displacement, that also given, right, into eta volumetric into n by 2, because it is 4-stroke cycle engine, right. So, that we would like to have mass flow rate, that is per second. So, this is kg per meter cube. If you multiply with displacement volume meter cube, you will be getting kg, but we need to get it kg per second, that is per second. So, cycle per second that we need to calculate, and that is n by 2, where n is the RPM. So, if n is rather RPS, sorry, if n is RPM, then again we have to divide by 3600. So, n is RPS, and this volumetric efficiency is multiplied, because we know very well volumetric efficiency is nothing but actual mass of air drawn into the engine cylinder to the theoretically mass that should have been drawn into the engine cylinder. So, actual mass of air should be equal to the theoretical amount of air that should have been drawn into the engine cylinder is the displacement volume into eta V. So, if we go to the next slide and if we plug in the value, we will be getting mass flow rate of air. So, for the turbocharged case is 1.537 kg per meter cube, then displacement volume is given 2316 centimeter cube into 10 power minus 6 meter cube. Volumetric efficiency is 91%, that you can recall, because we have discussed I think 2-3 times volumetric efficiency has got increased because of this turbocharging. Then 0.91 into RPS is 90 by 2, that is because 4-stroke cycle there are 2 revolution in one cycle. So, if we calculate it, this is coming as 0.145 kg per second. So, this is the mass flow rate. So, now let us refer to compressor performance. So, now we will refer to compressor performance. Because if we go to the problem statement once again, then we can see we need to calculate compressor speed, efficiency and finally heat transfer to the intercooler. So, if we need to know compressor speed, we need to use this performance map, and let me tell you the procedure of using this particular map to get some information about the compressor. So, if we go to the slide here, so compressor performance. So, for the compressor performance, this pressure ratio P2 by P1, that is the pressure ratio, that equal to 1.5, right. So, do not be confused 2 and 1. Now, 2 is the exit state of the compressor or exit of the compressor, and 1, the subscript 1 is used to denote the state at the inlet of the compressor, and subscript 2 is used to denote the states at the exit of the compressor. So, P2 by P1 equal to 1.5, and essentially we need to have this much amount of flow rate to be handled by the compressor. So, then mass flow rate of air is again 0.145 kg per second. Okay. So, if we need to know something for the compressor, that is what should be the efficiency of the compressor, if we can use the performance map, then it will make our calculation even more easier. So, what we can do now, let us go back to the slide wherein performance map is placed. So, by this time we know the mass flow rate that the compressor will handle, that is 0.145. We also know the pressure ratio 1.5. So, just if I use this color, so pressure ratio is 1.5, that is this line, and mass flow rate is 0.145. So, probably it would be something somewhere here. What we need to do? We need to draw one line which is parallel to the pressure ratio, that is y axis, but the line should pass through this particular point where mass flow rate will be 1.145. So, if we draw a vertical line, it may not be exactly equal, but we need to draw a vertical line like this, and we also need to draw another vertical line which will be parallel to x axis, and the line must pass through the point where pressure ratio is 1.5. So, again if we draw another horizontal line like this, then these two lines will cut the iso efficiency line in this performance map, and from there we can easily estimate what is the efficiency and then certainly speed. So, all these are speed, you can see 1300, 1600, 1800, and these dotted lines are iso efficiency line. Though I could not draw these two lines perfectly parallel to y axis and x axis, but what you need to do, you need to exactly get the point where these two lines will cross the iso efficiency line, and if I can identify that point on the iso efficiency lines, we can easily get the efficiency and speed of the compressor. So, for this particular case, as I said you that I could not draw them properly here, you will be getting eta isentropic efficiency of compressor, that is will be 70%, and speed of the compressor will be 1650 rps. So, these two data we will get from the performance map. So, I am writing here from the performance map. Let me repeat once again, efficiency or isoefficiency from the isoefficiency lines of the performance map you will be getting isentropic efficiency of the compressor is 70% and the speed at which compressor will run will be 1650 rps. Let me once again look at this and you can see that I could not draw these two lines perfectly parallel to y axis and x axis respectively, and hence this point could not be identified properly, but it is close to this, it would be somewhere here, and efficiency will be close to 70% and speed would be little higher than 1600 and that is 1650 rps. So, if I go to the slide wherein I have already mentioned, so these are approximately. Okay. Otherwise, you have to use isentropic relations to calculate all this data. Okay. Now, having calculated all this, then we can use the, so once the isentropic efficiency of the compressor is known, what we can do, we can use known, we can calculate exit or air temperature at the exit of the compressor. So, let us use it. So, if we write that exit temperature is T1 prime, then if the inlet temperature of air at the or temperature of air at the inlet of the compressor is Ti, then we can write this is P1 by Pi power gamma minus 1 upon gamma. Let me tell you one thing, else you can do one thing, instead of getting confused, we can write this is T2 T1. So, again I have to erase these two subscripts and we can write this is P2 by P1. So, P2 by P1, that is the rise in pressure of the air as it moves through the compressor, T1 that is ambient temperature, that is the temperature of air at the inlet to the compressor, that is 310 Kelvin, and this is 1.5 power gamma by gamma minus 1 upon gamma, and you can understand. So, gamma if we consider 1.4, so 0.4 divided by 1.4 and it is coming as 348 Kelvin. So, this is basically the temperature of air or air temperature at the exit of the compressor. So, this is the answer of the problem. Now, this is the temperature of air at the exit of the compressor, but if we go to the next slide, if this is the compressor, then we will be having, so this is P1 T1, so this is P2 T2, so this is exit, that is inlet state, and this is compressor C, but that air is not allowed to go to engine directly, rather it is allowed to go through aftercooler or intercooler, and then this is the temperature, let us say T2 prime, and that is the temperature of air which will be the inlet manifold temperature. Okay. So, actual temperature, if I can write actual temperature of air at the inlet to the intercooler of the engine will be something different, because so we have calculated T2, but actual temperature would be T2 actual, because we have estimated T2 assuming isentropic compression, but in a compressor actual compression process will not follow the isentropic one. So, if we try to calculate, so we know the isentropic efficiency of the compressor is nothing but here that is T2 minus T1, right. So, that is basically T2 minus T1, and from there we can calculate the actual temperature T2A, that equal to T1 plus T2 minus T1 divided by eta isentropic compressor, right. So, if that is the case, so this is 310 plus 348 that we have calculated at the exit of the air temperature at the exit of the compressor, minus 310 divided by compressor efficiency is 70%, that is what it is given. Let me go back to the problem statement once again, it will help you to get more confidence. So, you know that compressor, so what is the compressor speed and efficiency, and we have calculated the isentropic efficiency of the compressor, that is 70% from the performance map, that is why we have used. So, from this data we can calculate this, we have taken 0.7, and if we calculate it, it is coming as 364 Kelvin. So, this is basically the actual temperature at the inlet to the intercooler of the engine. So, hence from this we can say, from this data, heat rejected at the intercooler is m dot A into Cp air, assuming that Cp is not getting changed with that rise in temperature, into 364, that is the temperature at the inlet to the intercooler, and 340, that is at the temperature at the inlet manifold even after using turbocharger, right. So, this I can show you here, this is the temperature following isentropic expansion. So, 340 Kelvin, that because this is given 340 Kelvin. So, that is the inlet condition. So, if we calculate it, you will get the value. So, this is 0.145 into 1.005 kilojoule per kg Kelvin into 24, and unit should be kilowatt. So, the answer is coming as 3.5 kilowatt. So, this is the answer to the last part of this question. Let me go back to the problem statement once again. First, we have already calculated the brake power of the turbocharger, then we have calculated compressor speed, that is 1650 rps using the performance map. We could calculate isentropic efficiency of the compressor using performance map, that is 70%. Finally, using isentropic efficiency and the conditions of air before the compressor and after the compressor, we could calculate the amount of heat to be transferred to the intercooler, and the final answer is that we have obtained 3.5 kilowatt heat to be rejected. So, to summarize our today's discussion, we can see that we have solved one numerical problem on turbocharger. By solving this problem, we could establish the theoretical part or conceptual part related to this particular unit, and this problem has helped me to learn the use of performance map for estimating isentropic efficiency and speed of the compressor, knowing the pressure ratio and mass flow rate of air to be handled by the compressor. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.